Okay, thanks for joining my talk on pointer lifecycle types for lock-free data structures with memory reclamation. This is joint work with Roland Meyer. So to get us started, I'd like to go over a lock-free queue and discuss and see what this memory reclamation is all about. So as you can see, the queue is organized as a single linked list of nodes. Here the nodes are named A, B, and C, and there is a shared pointer head that points to the first node in the queue. To dequeue an element from the queue, the threads start out by reading the shared head pointer and creating a local alias. Then they search for the second node in the queue, and they do so by dereferencing their local alias of the head pointer and then following the pointer field of the node to acquire a pointer to, in this case, node B, which they call next. To actually update the queue, the threads execute a compare and swap, which atomically compares the local head pointer with the shared head pointer, and only if both pointers coincide, so only if the data structure hasn't changed, they perform the update and write the new value that is stored in next into head. So in this case, we move the head pointer from A to B, and we've successfully dequeued a node A from the queue. If you're writing this program in a garbage collected programming language, we can just forget about node A because the garbage collector will take care of it. If you're writing this, implementing this queue in an unmanaged language like C or C++, we have to manually delete A. So we have to delete it. The problem with the deletion, however, is that the first thread is still around and it still has a pointer to node A, which is going to dereference, which is not good because the dereference is prone to a system crash like a seg fault because it's accessing deleted memory. So what we observe in this particular case and in general with other lock-free data structures is that they perform an unsynchronized traversal of the data structure, which is why the deleting threads are unaware of dangling readers. And because it's lock-free, the dangling readers have no atomic mechanism to check whether a dereference is safe and actually performing the dereference. So in a nutshell, naive deletions are unsafe. So what can we do about it? There is something with quite a fitting name that is called Safe Memory Reclamation, or SMR for short. You can think of SMR as a library that is made available to the data structure that the data structure uses to do its memory reclamation. And all the memory reclamation logic is, so to say, hidden in this SMR library. So let's rewind our previous example and see what changes if we are using SMR. The first change is with thread 1. Instead of simply dereferencing its local alias of head, it protects its head pointer, so it protects node A. With this, it tells the SMR algorithm that it's going to access node A and that the SMR algorithm should not delete A as long as the protection is around. Then we continue and we, as before, we compare and swap and we update. We dequeue node A, and then thread 2 again wants to delete A. But this time it does not just call the explicit deletion, but it uses the SMR library and it calls a method that is called retire. So it asks the SMR library to reclaim A, but so the ASMR algorithm may choose to defer this deletion until it is safe. And in this case, it is safe only if there are no more protections on A. So in this case, obviously, there is a protection, so the SMR will defer the deletion, which is why the access or the dereference of the head pointer from thread 1 is safe, and it can safely acquire its next pointer to node B. Then it will perform as thread 2 before, its compare and swap, but this time the compare and swap will fail because the head pointer or the queue has changed. So nothing happens. It will just retry restart its operation and start by reading out the shared head again. And as before, it will now protect the new head, and this allows the SMR algorithm to finally reclaim node A because there are no more protections on it. So in a nutshell, SMR is basically about deferred deletion, and it does so by replacing explicit deletions with retires, and by threads that are going to read the memory, putting protections on the nodes. Now, if we want to spell out the code of this, it looks something like this in the garbage collected setting. So it's some 40 lines of code, and if you're interested, this is called the Michael-Scott's queue. And if we want to lift this program to SMR, we have to introduce, so to say, the calls to the SMR library, so the protections and the retirements. This is not too much additional code. It's some 6 lines of code. But we have to add the SMR implementation as well, which is another 40 lines of code. And with verification in the back of our mind, we already are a bit worried because it doubles the input size to our solver. But it's even more problematic here because the complexity of the data structure and the SMR implementation are comparable. So both are really complex programs that you cannot just look at and say, oh yeah, it's correct. And solvers have the same problem with that. So what are the challenges? What are the challenges if you really want to verify those kind of programs? Because these are log-free data structures, you have to handle an unbounded shared heap, you have to handle an unbounded data domain, an unbounded number of threads, all in the presence of fine-grained concurrency. And you have to face these challenges whether you're verifying the garbage collected version of the code or the version with SMR. Now, if we look into the literature, we find that people have actually solved the problem for these 4 challenges. And there are numerous works that give us techniques that work very well, and there are also tools that can automatically verify the GC version of the code that I just showed you. For the SMR version, however, we are facing 2 more challenges. First, we have to verify both the data structure together with the SMR implementation. But the real challenge is reclamation. So the tool or our technique has to reason about memory being reclaimed and reused. And the problem with that is that existing GC techniques do not work with that. So the techniques that we have for GC, they do not work at all, or they don't work really well. And in particular, ownership reasoning completely breaks when we face reclamation, and all of the techniques that are used on a GC, to my knowledge, heavily rely on ownership reasoning. So how do we verify those programs nevertheless? So how do we establish that the data structure together with the SMR implementation satisfies some property like linearizability, for example? The first thing that we can do is we can do compositional verification. So we can introduce an SMR specification and verify the SMR implementation against the specification. And then when establishing the property, we do not need to look at the SMR implementation anymore, but we can, so to say, replace it with the SMR specification. So to make this point visually, this is the code that we want to verify, and what we can do now with such an SMR specification at hand, we can, so to say, carefully throw away the right-hand side of the code and replace it with something like an automaton like this. And the nice thing here is that this automaton, it abstracts away from the implementation details of the SMR implementation. The problem with that is that we still have to reason about reclamation. And as I said, we don't really have efficient techniques for this. We only know how to do GC verification very well. So it would be great if we could just verify our data structure under garbage collection, and the result lifts up to our scenario where we use SMR. The problem with this is that for soundness, we have to establish that the memory reclamation does not introduce any additional behaviors. And how do we do that? Well, there is some property or condition that we call point arrays freedom. For this talk, you can just think of it as memory safety that ensures this. So if the data structure together with the SMR specification is memory safe, we are guaranteed that there are no additional behaviors and verification under GC is sound. That this is actually sound we proved in last year's POPL. So you might wonder why I'm around this year. And the answer is the point arrays check is really hard, and we could not solve it to our satisfaction, let's say. The problem is that we had to do a state space exploration so far, which had to address all the 6 challenges I showed you earlier. So we had to address the reclamation challenges, which make the solution of the state space exploration to check for this property really slow and inefficient. And this year, we overcome this problem. Our contribution is a type system that solves the pointer race freedom check. So a successful type check of our type system implies that the data structure together with the SMR specification is pointer race free. The cool thing about our type system is that the SMR specification is not hard-coded into the type system. Instead, it's a parameter to it. So it's like you're giving us the specification and we can instantiate our type system for your specification. Additionally, our type system is unaware of the shape of the data structure, so it doesn't care for whether it's a list, a stack, or a tree, or whatever. It externalizes all the reasoning about this into a garbage collection tool. So what we have achieved with our type system is that we can separately address the reclamation challenges, so the challenges 5 and 6 from earlier, separately from the GC challenges 1 to 4. And in the remainder of my talk, I'd like to give you a taste of our type system. And to do so, I'd like to do a, so to say, type check or more a type inference and visualize and show you what our types mean. To show you what our types mean, I need the SMR specification on the right-hand side. I tell you all the details about this when we need to. And I can use this automaton to visualize the types because our types reflect sets of states in this automaton. So whenever we have at a certain program location in our program a type, it means that any execution of the program that reaches this program location is guaranteed to take this automaton to a state that is represented by the type at that location. Okay, so let's get going. In the beginning of our type check, we start with a type environment that just contains the shared pointers. So we only have the head pointer, and its type is empty. So we do not know anything about the memory that is referenced by this pointer. So at the right-hand side in the automaton, this no knowledge means that we could be in any state of the automaton. Reading out creating a local alias of the pointer just copies over the type binding, so we end up with both pointers having the empty type. Next, we see a protect of the local copy, so of the small head. And if we look into the specification, we see that it, so to say, reacts on the protection. So because the protection is some API function of the SMR, the specification of the SMR reacts on it. For example, it would take us from state S0 to state S1. States that do not have an outgoing transition labeled with protect, we interpret as that we stay in those states. So what we end up here is that we are guaranteed to be in one of the four states at the right, and we call this type P because we are now guaranteed that the head pointer or the memory that it references is protected. So back on the left-hand side, we say that we add this type P to the lowercase head. Entering the atomic block does not change the type environment. It just gives us some more reasoning power because we know that there are no interferences. Next, we have an annotation that says active head. So what this annotation means is it means that the head pointer has not been retired yet. We call this active. And as a result, we add the type A, standing for active, to the shared head pointer. You don't need to worry about these annotations. We assume for the type check that they are correct, but we can actually automatically discharge the correctness of these annotations. So in our paper, we have an instrumentation that takes the code into a garbage collected version so that we can discharge those kind of annotations under garbage collection, so with existing tools. Next, we have an assumption. So this is basically an unrolling of an if loop that says that both the local copy and the shared head are equal. So we combine the types. So we end up with P and A. So for the moment, you have to believe me that this is actually the set of states that are captured by A. And what we can do is we can compute the intersection. The problem with this is that there is an R transition here, which is explained at the bottom, which means that a retire of the thread that we are typing or any other thread can take us out of the green region. And because our types, because we're eventually leaving the atomic block, we need to care for interference, so we have to add the state S5 and end up with this green area, which we call type S. Leaving the atomic block, we lose the type of the shared head pointer because due to interference, the shared pointer could be modified, could be redirected to another node, so we do not know anything about a potentially new location. The important thing here is the dereference in the next line. To show memory safety or point arrays freedom, we have to show that the dereference is safe. So how do we know from type S that the dereference is safe? And we know this because while we're in the green area here, F3, so transitions labeled by F, take us to the final state, to state S2. And in the specification of SMR automata, we interpret these final locations as behavior that the SMR implementation does not exhibit. So this is a negative specification. Whenever we reach a final state, we know that the SMR implementation does not do this. So in this case, we know that F3, so that the SMR will never execute F3 in this setting. So we know that the dereference is safe, and we know that the program is memory safe. The type check of the method will now continue, but there are no more dereferences, so the interesting part is over. So we can conclude that the function is point arrays free or memory safe. To give you a quick overview of our approach again, so what we start with is the SMR implementation and the data structure. We turn the SMR implementation, so to say, we lift it to the specification and turn it into types, and then we execute and we perform the type check. After this, we take the data structure code, we instrument it, so instrument it to check annotations, which yields a garbage collected program, which we can just throw into an off-the-shelf verifier and check the annotation. So it's basically checking for assertion violations. And lastly, we can strip away any SMR code from the data structure and verify the data structure as a GC version, and also use an off-the-shelf verifier for this. Yeah, we've implemented this, and the runtimes are amazing. So in our previous work, it took like several hours to verify the running example, while we now take only 20 seconds. Thank you.
Thank you, Sebastian. So there's a first question there.
Hi, thanks very much for your talk. So you mentioned a couple of programs that you can verify. Are there programs that are memory safe but you can't verify using your type system?
We have some, yeah, there are programs that we cannot verify, but it's not due to our type system being too weak or not able to verify them. It's because that our verification backend, so the off-the-shelf verifier that we use, cannot establish, for example, the annotation correctness. I mean, this is our biggest problem, that verifying the annotations or then in the end linearizability times out or is too imprecise.
You use these automata to describe sort of the life of the pointers, and this reminds me of protocols in logics like Iris. Can you say whether you could use this to maybe construct the protocols in Iris or infer part of them?
I'm not an expert in Iris, I have to admit.
Fair enough. Neither am I.
I mean, what you need to do is, I mean, you could execute the type check, and then from the type check, you basically know which types you need doing the execution, right? And I mean, maybe you can even encode the automaton in Iris. I don't know if this is possible. So if you have the automaton, the type is basically just a set of states. I mean, I don't know. I mean, I don't know how Iris works, but if you can just encode the automaton inside Iris and use the types as the sets that reference states inside the automaton, I think you should be good.
So can I ask a question myself? Maybe
Sure.
maybe a bit naive. So this automaton, where does it come from? Is it inferred or is it
No, at the
provided?
moment we cannot infer it, so we, so to say, take it for granted. So you have to give us this automaton, but so in our previous work we also showed that you can verify that the SMR implementation adheres to the specification.
Okay, so any final question? Okay, so then let's thank Sebastian again, and this is the end of this session.